Okay, so I think we are hopefully now live. Hello everyone, welcome back to another edition of Quarantine Thermo. We're very pleased to welcome Professor Alessandro Silva from CISA. Alessandro is an expert in all aspects of non-equilibrium quantum statistical mechanics. Okay, I'm not going to try and riff through all of his achievements, but many of you will, of course, be familiar with his kind of pioneering work on work fluctuations in many body systems. But recently, Alessandro has been doing some very, very nice work on thermalization in collaboration with our group in Dublin, and I think he's going to tell us a little bit about this work and an update on the progress. So before I hand over to Alessandro, I'll just do my usual thing. I will basically just explain the format. So Alessandro is going to speak for however long he wants, uninterrupted. And then at the end of the talk, we're going to have questions. So if you do have any questions during the talk, please just write them in the YouTube chat window, and I will ask them to Alessandro at the end. And if you can please just write your name with the question if it's not already clear from your YouTube username. Okay, so with that sort of all said, I'm going to hand over now to you, Alessandro. So please take it away.
Okay, thanks, Mark. Thanks everybody for being here today. So I'm going to tell you something about some recent work that we have done with Marlon Brenes, Silvia Pappalardi, and John on essentially using the quantum Fisher information to sort out an interesting problem in non-equilibrium physics, that is to be able to see correlations beyond thermal in a state that looks thermal from all local points of view. So before entering the details of what I would like to tell you, let me start with a rather long introduction on the subject. As you will see, I mean, this is supposed to be a kind of blackboard lecture, so I'm going to be rather pedagogical in the beginning, but I'm going to skip a lot of details of the calculations because, well, this is not supposed to be a lecture. It's supposed to be a seminar. Anyway, so the topic I'm going to discuss today is in the broad field of the study of the dynamics of thermally isolated quantum many-body systems. Now, this is a subject that has been of interest in condensed matter physics and statistical mechanics for decades, but became much more interesting in the past 20 years, essentially because of experiments, and because of the fact that experimentalists were able to create systems that for the time scales on which experiments are performed are essentially thermally isolated. And examples of such systems are cold atoms in optical lattices and, for example, ion traps, but there could be others. I mean, I'm not pretending these to be the only possible systems on which these experiments can be done. Now, the important ingredients from a theoretical point of view that you want to have to study statistical mechanics in these systems are the combination of quantum coherence. The system should have a pure, nice unitary evolution. Then you want to have many-body interactions. Possibly, the effect of strong correlations is sometimes interesting in these systems. And at the same time, you want to have some kind of non-equilibrium driving. Now, there are many types of non-equilibrium driving you can apply to such systems, periodic fields or whatever. But one non-equilibrium protocol that has been studied a lot in the past, I would say 15 years, has been the so-called quantum quench. The name was coined by Pasquale Calabrese and John Cardy in a famous paper in 2006, if I remember correctly. And quantum quench is essentially the following. Imagine that you have a system with some Hamiltonian that depends on a parameter lambda. Lambda could be, for example, the strength of interactions or the depth of a lattice potential, such as what happens for atoms, cold atoms in an optical lattice. And you're able to vary this parameter in time abruptly from some initial value to some final value. Now, from non-equilibrium perspective, this essentially realizes a situation in which you start your time evolution from the ground state of your Hamiltonian with the initial value of your parameters, and you time evolve this initial state with the final Hamiltonian with lambda f. And you want to see what happens. Now, among the various, then you have to ask yourself, how do I characterize the time evolution of these systems? Now, tons of ideas have come up in the past 10 years on various types of characterization of non-equilibrium evolution after quantum quenches. So let's keep today just a straightforward condensed matter-ish perspective. What a condensed matter experimentalist would do is just pick up his favorite local observable O, and then measure, for example, its average and the time evolution of the average itself. Now, quite frequently, this time evolution, if, well, I'm going to say words that I don't have time to explain too much, but if essentially the point spectrum of the observable, the local point spectrum of the observable is continuous, then this time evolution will essentially attain a stationary state that is well defined. So there is a limit for t going to infinity. And the question is how to characterize this limit of the observables. Essentially, let's call this limit O infinity. Of course, it's going to depend in general on the initial state that you have, but how do you characterize? Well, first of all, this limit, if it exists, is equal to the time average of the time evolution. So you just take this integral. And in addition, if you do this time average, it's very simple to show that it's going to be equal to the trace of O with something that is called the diagonal ensemble. What is the diagonal ensemble? If your system does not, your Hamiltonian does not have degeneracies in the spectrum, you just pick up the coefficients of the representation in the eigenbasis of the Hamiltonian of your initial state, you square them, and you multiply by the projectors. And this is your effective ensemble that describes the long-time dynamics. Now, all right, so, well, this is one thing you can do, measure the time evolution of observables, and in general, you will see perhaps something that oscillates in time and then goes to a stationary state. Another thing you could do is, for example, measure correlation functions of observables. And again, you can ask yourself how correlations look like at long times, for example, by introducing this kind of Wigner-like representation and asking yourself, what is the limit of this correlation function for large times, for large average times, and whether you're able to reproduce this limit by some effective ensemble, and so on and so forth. Now, these kind of questions have been addressed, essentially can be summarized in the question of how to describe effectively the stationary state of the dynamics. Effectively, by effectively, I mean the following. Essentially, when you time evolve your system, you're always in a pure state at all times. So what an effective stationary state means is the state that is effectively seen by local observables. All right, so this kind of question has been addressed for two broad classes of systems. The first class are integrable systems. And integrable systems are special because they have as many constants of motion as the number of degrees of freedom. So you essentially have a set of constants of motion ij that are local and all commute with the Hamiltonian. And then you can easily expect that if this happens, your system will not just keep memory of what was the energy you put in initially when you made your quench in the system, what is the average energy you just threw in a physical system itself, but will keep memory also of the initial value and the initial state of all the concepts of motion. Of course, I mean, these are conserved quantities. And in particular, what you're going to have, what you should expect is that O of t will tend asymptotically to something that is called to the average, to a stationary value that is just reproduced by the trace of O with an effective ensemble that is called a generalized Gibbs ensemble, GGE. And that is just a maximum entropy ensemble that is consistent with all the constants of motion that you have in your Hamiltonian. Now, this is a kind of obvious statement. It can be expected on the basis of what Jaynes taught us in 1957. But interest on this generalized Gibbs ensemble resurfaced in physics, essentially following famous experiments by Kinoshita et al. In the group of David Weiss in Pennsylvania, essentially observed the lack of thermalization in a Liebig gas that was thrown out of equilibrium by essentially splitting a one-dimensional clouds into two parts. And later on, it was conjectured and later on verified by a number of works, analytical works, by Rigol et al., that indeed the stationary state of the dynamics could be reproduced using a generalized Gibbs ensemble. Now, this is a very long story. It took about 10 years, up to, I would say, 2015, to realize how to write down properly a generalized Gibbs ensemble for a generic integrable model. I mean, a non-trivial one, not just a model that maps into free fermions of free bosons. But eventually it was figured out which IJs to put in by essentially specialists in integrable systems. And if you want to read about this, I think the paper that puts an end to this story is the paper by Ilievsky et al. In 2015. All right, so far for integrable systems. Now, the story of non-integrable systems or generic systems is much, much older because, well, this is an interesting and important problem in physics. In practice, the problem you're asking yourself for a generic system is the following. Suppose that you start your time evolution with an initial state which is a coherent microcanonical superposition. What I mean by microcanonical is that the Cn is not equal to 0, is different from 0, provided provided En is in between, is in a microcanonical shell centered around energy E. Then, I mean, if you start the time evolution with such state, you should expect that if the system will be able to thermalize at long times, then what this should mean is that O of t, as t tends to infinity, will go to a stationary value that is essentially given by the trace of O with the microcanonical ensemble, which, if O is a local observable, just by equivalence of ensembles, we are dealing with systems with short-range interactions, etc., is going to be just the plain trace of O with a Gibbs ensemble with inverse temperature beta. Now, of course, I mean, you could realize this if you impose that your diagonal ensemble, the one I wrote down in the previous slide, this one, is identical to the microcanonical one. But this is too strict of a requirement, because it would impose that all the Cn are equal, essentially satisfy the equal a priori probability. So they are equal in absolute value and equal to 1 over the number of, and equal to 1 over the square root of the number of states in the microcanonical shell. So this would mean that just if you define this as thermalization, as the requirement for thermalization, just a few initial states will be able to ever thermalize. This is fortunately not the case. And the formal requirement, theoretical requirement to see thermalization was actually discovered by Mark Srednicki in 1994, following some works by Deutsch in 91 with basic idea that were essentially the same. And the idea of this so-called eigenstate thermalization hypothesis, so that encodes essentially the requirements of that an observable should satisfy in order to look thermal upon the quench from a microcanonical superposition that I just described, are the following. You want that your matrix elements of your observable in the basis of the Hamiltonian are essentially made out of a smooth function in the diagonal component of phi, where E is just the average energy. So E here will mean En plus Em divided by 2, plus the off-diagonal matrix elements that are essentially, apart from a normalization factor that will contain the microcanonical entropy in the exponent, and another smooth function of E and omega, where omega now is the energy difference, will contain also a factor R and M that is random. I mean, what I mean is that essentially if you take statistics of these matrix elements in a system, in a kind of narrow energy shell that contains enough states, the off-diagonal matrix elements will look like a pseudo-random set of matrix elements with this factor RNM that is going to have zero average with respect to this randomness and unit variance. Now, these are the two requirements that you have to ask in order to observe thermalization. Now, in practice, it seems that, well, frequently this RNM has Gaussian statistics altogether, but this is not a requirement. So, given this, what will you see in your system? So this is the eigenstate thermalization hypothesis in the most general form. Now, what will you see? Well, if this is true, then you can prove two things. First of all, you can prove that you're starting from a microcanonical superposition, as I was telling you before. As you take the limit of t going to infinity, your time evolution of the observable will essentially tend towards the diagonal component of these matrix elements at the average energy of your microcanonical superposition. And this is, by the way, equal to trace of rho microcanonical times O. Well, this is a kind of trivial statement, if you want. I mean, the moment you assume that your diagonal component is a smooth function with fluctuations that are exponentially small in the system size, if you consider a finite size system, then of course this has to be satisfied. What is much less trivial is that an experimentalist, when he thinks about thermalization, will not just think about, for example, the time evolution of an observable as in this instance here, but another test for thermalization he could make would be, for example, to check whether the fluctuation dissipation theorem is satisfied or not. So what he would do is measure the response function, chi tt prime, which is minus I theoretically defined as minus I theta t minus t prime times the commutator of O of t and O of t prime. and then measure the symmetrized, well, essentially the noise fluctuations, which is just a symmetrized correlator, delta O of t, delta O of t prime, where by delta O of t and t prime, I mean the deviation from the average value. And now what you can prove, and it's an interesting exercise that I advise you to do if you're interested in learning how to use the eigenstate thermalization hypothesis, you can easily prove that if you look at if you apply the eigenstate thermalization hypothesis the way I wrote it up above, and take the Fourier transform of these functions, then S of omega comes out to be 4 pi times the cosine hyperbolic of beta omega over 2 times the absolute value squared of the smooth function that was describing the off-diagonal matrix elements. So that's the physical meaning of that smooth function. It's essentially encoding correlations. And at the same time, the imaginary part of the response function, of the Fourier transform of the response function, which is the object that essentially controls energy absorption in the system, is going to be equal to 2 pi times the sine hyperbolic of beta omega over 2 times f of e and omega squared. And now you see something interesting. If you combine these two expressions, you easily get that because the two are both proportional to the absolute value squared of f of omega, so that's essentially what is encoding these two correlation functions, that implies that the fluctuation dissipation theorem is going to hold. So S of omega is 2 cotangent hyperbolic of beta times omega over 2 times chi double prime of omega. So essentially, what I wanted to say is that if the eigenstate thermalization hypothesis is true, then your system, for your observable, and typically, when you have a generic system for which you expect to see thermalization, so it's ergodic and so on and so forth, of course, the eigenstate thermalization hypothesis is not going to be observed for all observables. It's going to be true for special observables which are local in space typically, or just the most general are called few body observables, but it would take me too long to explain what they are. So anyway, if you look at your system with such local observables and you measure 1-point functions and 2-point functions, so essentially averages and correlators, you will see your system as thermal, no matter what you do. You will see fluctuation dissipation theorem, you will see microcanonical ensemble. So in practice, you're in a situation that is described by this cartoon. It's as if you have a black box, and inside your black box you have a pure state that depends on time, your pure state after quantum quench. This pure state is fully quantum coherent, has all the many-body interactions, etc., etc. But then you make a hole on the side of your box and you look inside, and the way you look at it is just by local measurements. And in practice, is as in this famous painting by Roy Lichtenstein, in which, he says, I can see the whole room and there is nobody in it. Well, in our case, there is only thermal noise. So you see just plain thermal noise and nothing else. And now you can ask yourself, okay, but this is a pure state. So can I see correlations that are beyond just this thermal noise? Well, this question was asked by a number of people recently and became a kind of topic of research by itself. One of the guys who asked this question in a clear way that I particularly like is Alexei Kitaev. I'm a fan of his YouTube. Since we are on YouTube, I'm a fan of his YouTube talks. In particular, one he gave for the Fundamental Physics Prize in 2015. in which he was interested in looking at practically at this problem from the point of view of black holes. So the problem of black holes is very similar. You want to find an analog of a black hole that is essentially a pure state from a theoretical point of view that emits, that from a local measurement, essentially by the radiation that is emitted, looks thermal. And he asked himself the question, how do we tell that this system, whether this system is a black hole, a true black hole in pure state, and not just some piece of junk? And by piece of junk, I mean something that has just thermal noise, okay, using the words of Kitaev. Well, so his proposal was to use, following essentially the ideas of Schenker and Stanford a couple of years before, to use what is called a out-of-time order correlation function to detect these non-thermal correlations. That is defined as follows. If you have two local observables, A and B, that, let's say, initially commute, so for example, they have support that is separated in space, then you take the commutator, you let one evolve in time, you take the commutator and you square it. Now, why this is an interesting object to look at? Well, it's essentially something using which you can characterize quantum chaos. This is something that was known already in 1969, chaos, 1969 by Larkin and Ovchinnikov. And the reason you can expect this to be connected to chaos is essentially the following. If you have a system, a one-particle system, and you take the correlation, the commutator between pj at time t and p, let's say k at time 0, well, this is equal to I h dp dxj, dpj dxk, and you can expect this to grow exponentially in time if you have a chaotic system, essentially because of exponential sensitivity of the trajectories to initial conditions. So this is going to go like I h bar times e to the lambda t, where lambda is the Lyapunov exponent that characterizes your system. So in practice, for such single particle systems, C of t is expected to grow like h bar squared e to the 2 lambda t. So this exponential growth of the out-of-time order correlation function is a signal of the presence of quantum chaos in the system. And in addition to this expectation, there were some recent works, in particular by Kurchan and Foini, and by Murthy and Sredniki, who essentially had the idea that the out-of-time order correlation function in practice, this exponential growth of the out-of-time order correlation function might be connected to the fact that the out-of-time order correlation function cannot be reduced to products of two-point correlation functions that can be obtained by the eigenstate thermalization hypothesis. So in practice, said in simple words, the out-of-time order correlation function detects correlations that are beyond the eigenstate thermalization hypothesis, okay? And that's why, I mean, that's how this is connected to quantum chaos and to seeing something that is not thermal junk. In particular, it was conjectured that the Lyapunov exponent for a generic many-body system should be always smaller or equal than 2 pi times the temperature, the effective temperature of the system at which it would eventually thermalize. All right, so now I'm essentially at the end of my pretty long introduction. But I think I explained rather well what is the problem. So now I would like to, for the rest of this talk, I would like to convince you that it's not, I mean, the out-of-time order correlation function is a very interesting object by itself, but if we want to have something that distinguishes between a pure state that looks thermal from all local measurements and a true thermal mixed state, there is another object that we could employ, which is the quantum Fisher information. And the quantum Fisher information, as some of you might know, is an object that is connected in particular to the physics of multipartite entanglement. Now, it's kind of obvious that if you want to see something about, to detect the fact that you're dealing with a pure state that keeps track of all coherences and of correlations and distinguish it from a mixed state, you should look at something like entanglement. The funny thing is that if you look, for example, at the time evolution of the entanglement entropy, then, well, that's not enough, because the entanglement entropy is known to grow in time for a typical system with short-range correlations. When you make quantum quench, it starts from some initial value, it grows in time, and eventually saturates to some value. If it's the entanglement entropy of an interval with respect to the rest of the system, saturates to some value that is essentially proportional to the length of the interval. So if you have a system in higher dimensions, it's going to be proportional to the volume. So in practice, what I want to say is that the entanglement entropy in the stationary state will look like the thermal entropy from all points of view. So in practice, it's not enough to discriminate between a pure state that looks thermal and a true thermal state. What could work instead is the quantum Fisher information. So in the remaining few minutes of this talk, I would like to try to explain what the quantum Fisher information is quite briefly, and then try to convince you that indeed it does what it's supposed to do. It tells you that it distinguishes pure thermal states from mixed thermal states. So what is the quantum Fisher information? Well, the classical Fisher information is an object that is used every day by people doing statistics in order to figure out, when you have a model in statistics, essentially you assume that your data are described by a probability distribution p theta of x, where x is the variables you're observing and theta are the parameters of your probability distribution. The Fisher information tells you with which accuracy, by measuring just x, you can infer the value of the parameter theta. And that's it. And in particular, so if you want to understand it in simple terms, think about two Gaussians and think about the problem of discriminating two Gaussians which are centered at different points by just measuring the outcome of the probability distribution x. Well, of course, the accuracy with which you will be able to determine the center of the Gaussian is set by the width. I mean, that's the limit that you have. In general, if you want to determine this accuracy, you can, well, Fisher, I think his name was Ronald, but Mark might know better than me. What is the name of Ronald Fisher? He was working in England in the first. Well, I mean, he discovered the Fisher information in the first part of last century. Anyway, so he came up with the idea of characterizing this accuracy using f of theta, the Fisher information that for classical probability distributions is nothing but the derivative of the log of p squared times p. So it's essentially the average of the derivative of the information that is associated to the probability distribution squared. And now, well, you can see that this is the function that does the game that I mentioned before, simply because if you compute it for a Gaussian, then it's a matter of straightforward calculation to show that this is 1 over sigma squared, where sigma is the width of the Gaussian itself. And in addition to this, you have a quite famous theorem that is called the Cramer-Rao bound, that tells you that the variance delta theta squared of the estimate for your parameter theta is always greater or equal than 1 over m times f, where f is the Fisher information and m is the number of times you repeat a measurement of x. All right, so now what about, and in particular, of course, there is an estimator that saturates this bound that is in the maximum likelihood, but these are all details that we don't care about. Now we want to talk about multipartite entanglement. So let's switch to quantum mechanics. In quantum mechanics, the problem can be posed in a similar way. Suppose that I have a density matrix, a generic density matrix. So let me write it in this way. And suppose that I now rotate this density matrix by a rotation generated by an operator O. I know what is the operator, but I don't know by which angle I'm rotating the density matrix. I don't know theta. And now by performing measurements on rho, I want to infer what is the value of theta. So for example, I could perform repeated measurements using a POVM on rho and try to infer what is theta from the outcome of these measurements. Well, it turns out that there is something similar to the Cramer-Rao bound that tells you that the variance of theta, this estimate, is going to be always greater or equal than 1 over m times f of q, where m is the number of times you repeat your measurement, exactly as before, and f of q is the quantum Fisher information, which in our case, for a generic density matrix, is going to be equal to sum over ij of pi minus pj squared divided by pi plus pj times the absolute value squared of the matrix element itself. All right, so now this quantum Fisher information has a beautifully simple expression if you're dealing not with a generic density matrix, but with a pure state. If you're dealing with a pure state, not surprisingly, I would say, because essentially it tells you that the Cramer-Rao bound is something similar to an uncertainty relation, then you will find that your Fisher information for a pure state is equal to 4 times the fluctuation on your pure state, I don't know, let's call it naught, of the operator O. It's very easy to prove it, so I mean, I don't think we have to go through these details. In which case, for a pure state, you see immediately that, as I was telling you before, the Cramer-Rao bound can be written in this way. And now it should look pretty much familiar to you. So for m equal 1 is essentially an uncertainty relation. Now, let's see now what is the connection between the quantum Fisher information. How much time do I have, Mark? Okay, so let me take another 10 minutes. All right, so 10, 15 minutes. All right, so let us see now what is the connection between the quantum Fisher information and multipartite entanglement. Well, in order to see this connection, suppose that we perform the following experiment. Let's take O to be, well, let me change color. Let's take O to be just a sum of local operators, for example, spin operators. And let me take my state, my pure state, to be just a product state of, various single spin state of my essentially uncorrelated spins. Well, it's evident that when you think about the expression for the Fisher information that I wrote down here, since we are dealing with uncorrelated spins, right, then f of q is going to be equal to n times some number. Let's call it a Fisher information density that is not going to be a number, is not going to scale with n in any possible way. That's just a result of the fact that the fluctuations the system is completely uncorrelated. So the fluctuations of each single spin are independent. And therefore, what you get is that the accuracy that you will get on your phase estimate is always greater or equal than 1 over m times n times f of q. Now, this is what is known for. This is what is known, well, why for? No, not for. This is what is known as the shot noise limit of quantum metrology. So it's essentially what you can get when you take a many-body system in which all degrees of freedom are uncorrelated. Suppose that now, instead of taking uncorrelated degrees of freedom, we take them in the most, I would say, quantum correlated way. So we pick up a GHZ state, like this one. And now we ask the same question. How do the fluctuations of our local operator look like on this state? Well, pick as your favorite local operator just the sum over I of sigma zi. And it's not hard to convince yourself, well, that of course the average of O is going to be equal to 0. But at the same time, O squared is going to scale like n squared. And therefore, what you will get in this case is that delta theta squared is going to be greater or equal than 1 over 4 times, sorry, 1 over, yeah, there was a factor of 4. Oh, well, 1 over 4 times m times n squared. Okay, so this is called the Heisenberg limit. So now you see something interesting. In practice, this tells you that the scaling of the Fisher information with n gives you information about how many degrees of freedom are entangled. If the Fisher information scales like just n itself, then you have at most a few degrees of freedom that are entangled in your system, but you could have just a product state and that's it. But if it starts scaling like n squared, then as in the GHZ state, you will have a number of degrees of freedom that are irreducibly entangled that is as large as the system size. Now, all of this can be encoded into a theorem that essentially tells you the following. If I pick now a generic spin system and pick a generic operator that is a superposition of spins in various directions and I, and construct the quantum Fisher information that is the maximum over the set of the randomly chosen set of these versors of these operators all, of the Fisher information for these operators all, then if the Fisher information density associated to f of q is greater than k, then this means that your system is k plus 1 entangled. That is, it has a number of degrees of freedom that is that are irreducibly entangled, that is essentially equal to k plus 1. The definition of multi-partet entanglement is somewhat technical, but let me skip it. I think you understand what I mean from the previous example. All right, so now we can play the game of taking this quantum Fisher information and the idea of quantum Fisher information, its connection to multi-partet entanglement, and try to apply it to thermal mixed and pure thermal states and see what comes out. Let's start with a Gibbs ensemble. So the idea of figuring out what is the Fisher information for a Gibbs ensemble was actually is something that is a calculation that was performed first by, I think, Marcus Heil, Tagliacozzo, Zoller, perhaps someone else. I apologize, I didn't write up the reference a couple of years ago. And essentially what they figured out is that if you start with a density matrix rho, which is thermal, like this one, and compute the quantum Fisher information for this density matrix, then you will find it's a very simple calculation. So I'm sure that many of you will be able to reproduce it just on the back of an envelope. You will find that this is equal to the integral in the omega of the tangent hyperbolic of beta omega over 2 times the imaginary part of the response function chi of omega. We defined the response function before, so it's essentially the same object. How do you prove this? So if I want to prove it, let me quickly tell you. You just take this definition. This is the expression for the quantum Fisher information that was found in a famous paper by Braunstein and Caves. And you substitute for pi the Boltzmann weights. And then you just have to compare this with the Lemon representation of your correlation functions, and you will see that the two match perfectly. So this is equal to that. All right. In particular, if you now take this expression and apply the fluctuation dissipation theorem, that should be valid because we have a system that is in a thermal state, then you see that this is equal to 1 over pi times the integral in the omega of the tangent hyperbolic squared of beta omega over 2 times s of omega. So here I just applied the connection between s of omega and chi prime of omega that we wrote down in the previous slide. All right, so this is for the Gibbs ensemble. Now, what is interesting and what we figured out with Silvia Papalardi, Marlon Brenes, and John Gould is that if now I take a system that is not in a Gibbs state, but is actually in a microcanonical superposition, it's actually performing a time evolution from a pure state, from a microcanonical superposition after a quantum quench that at long times thermalizes, and I look at it with an operator that satisfies ETH, then my Fisher information for the pure state is going to be equal to 4 times delta O squared, and in particular this is 1 over pi integral d omega s of omega. Well, now you see, if you compare the two, so F pure is always greater or equal, at most, than the one relative to the mixed state, right? Because the tangent hyperbolic is always smaller than 1, smaller or equal to 1. So this inequality is always satisfied. F Gibbs. Now, this is an interesting statement. It means that even though these two states, from all local points of view, right, from all local measurements of correlation functions, of local observables, etc., look pretty much the same. Well, first of all, their entanglement content is different, but not only that, they are also different, for example, in their usefulness for quantum metrology. In particular, you can see this by just looking at an expression that is very similar, by re-expressing the quantum Fisher information for the pure and for the Gibbs state in terms of the response functions, chi-double prime. In the original paper by Zoller, Tagliacozza, and Heil a couple of years ago, in which they essentially derived this formula, they attempted to look at signatures of finite temperature phase transition in the quantum Fisher information for the Gibbs ensemble, and they found none. There are no signatures whatsoever for a classical phase transition. Now let me show you why this happens. So, and let me show you what happens for the pure state. That's quite intriguing. So if you rewrite everything in terms of the response function, you find that this is equal to 2 over pi integral d omega of cotangent hyperbolic beta omega over 2 chi double prime of omega. And this one instead is equal to 2 over pi integral d omega of tangent hyperbolic beta omega over 2 chi double prime of omega. Now, suppose that you have a system that displays a phase transition at finite temperature, right? So these are your system parameters, let's say lambda, and this is temperature. And then you have a phase diagram that looks like this one, in which you have one phase sitting here, another phase sitting there, separated by a second order phase transition, right? And imagine that you make a quantum quench, which has, so you put an extensive amount of energy in your system, and this energy corresponds to some effective temperature T. And, well, you change, you vary lambda or you vary T, I mean, it depends what you do, but you essentially put your system close to a critical point, right? You can do this by also, thinking about pure states in principle, right? Making a quench and looking at the time evolution of a pure state. You would call that a pure critical thermal state. All right. So close to a critical point at finite temperature, it's pretty well known that chi double prime of omega will, unlike what happens in other phases, will tend, as omega tends to 0, to some finite value. And that signals the fact that the system becomes gapless, and in practice, you're able to absorb energy with any periodic drive, no matter what is the perturbation you put in, what is the frequency you put in. Now, this tells you something interesting. If you have a response function that has this property at close to 0 frequency, you see that for the pure state quantum Fisher information, this has absolutely no consequence whatsoever, because here you have a tangent hyperbolic that always vanishes as omega tends to 0. But for the pure state quantum Fisher information, actually, because of the presence of this cotangent hyperbolic that blows up as omega goes to 0, you will start getting a divergence. And in particular, well, this divergence will turn out to reflect a scaling of your Fisher information with the system size. You will be able to prove that for the pure state, the quantum Fisher information will go like n to the power gamma over mu times t plus 1, where gamma and mu are the critical exponents of the second order phase transition we are dealing with. Is the dimensionality, and n is the number of degrees of freedom. Now, what does this imply for metrology or for multipartite entanglement? Well, let's take the quantum information density, the Fisher information density. So let's take the ratio of this to n, and this will go like n to the power gamma over mu d. And now if you play around a bit with scaling relations for critical exponents, you can rewrite this as n to the power delta minus 1 delta plus 1, where delta is the critical exponent for the critical isotherm. So in practice, you see that the limiting value for f of q is n itself. So that's at most the scaling that you can get. And therefore, the Heisenberg limit is the maximum, right? You can have as many degrees of freedom that are entangled as the number of degrees of freedom itself, but that's at most what you can get. In general, you will get a scaling that is of f of q that is subextensive, but, well, that's to be expected. That will depend on the critical exponent delta. There is another interesting thing that you can do with this, and this was actually a heavy task for our study, was to actually prove that all these ideas are not just interesting theoretical ideas, but actually pertain to real systems. And in particular, what I'm showing you here are numerical calculations, essentially exact diagonalization, done by Marlon Brenes, who is really a master of this type of calculations. He's a student in Trinity College Dublin. What was done was to take an XXZ quantum spin chain, the Hamiltonian, you see it here, and since the XXZ model is one way to do that is to add a staggered field like this one, right? And then what happens is that when you do this, you can study, for example, what is study the problem that I just discussed. And you start your time evolution well, you pick up a state in the set of eigenstates of this Hamiltonian that has an energy density that is consistent with a temperature that you choose. In this case, for example, the temperature was chosen to be T equal 5, and then in appropriate units, and then you figure out whether your ETH works or not. And as you see, it works beautifully. This is the response function calculated from the ETH state, so a state with this energy density with an effective temperature T equal 5, compared to the one calculated using the canonical ensemble with the temperature set by the energy density. And you see that the two match pretty nicely, right? Up to some small wiggles that might be connected to finite size effect. Consider the fact that these are system sizes that are still relatively small, 20 sites. Now, what you see on the right hand side are the calculations of the quantum Fisher information and the quantum Fisher information density for the operator O, that is essentially the staggered magnetization, and for different system sizes. The parameters are chosen in this way. Essentially take the system in the critical phase. And now what you see is that if you look at the Fisher information density, you see how different is, as a function of temperature, the behavior of the Fisher information density for the pure thermal state, like this one, and the behavior of the Fisher information density for the associated Gibbs state. In particular, for infinite temperature, the pure thermal state has a Fisher information density that is finite, while the other one, the Gibbs state, has a Fisher information that is equal to 0. And, well, that has, of course, implication, as I explained to you, for both for multipartite entanglement and for metrology. In practice, this calculation shows uniquely that the two quantities are very different on pure and mixed states, even though you're not able to distinguish them, as shown here, by performing local measurements. Okay, so Fisher information is just like a magnifying lens to see the structure of quantum states. So to conclude, I apologize for taking a bit more of the time that I was supposed to take, but so I hope I explained what is the problem we try to address, essentially how to distinguish a pure thermal state from just some quotation marks thermal junk. And I hope I convinced you that the Fisher information, the quantum Fisher information, does the job pretty nicely. Now, whether it's the only quantity that does the job, whether there are other quantities that are better suited for experiments, and whether it can be applied to distinguish other effective ensembles from their pure partners, is something that has to be studied. And, well, we are presently doing some work on this, but I expect that some others will pick up from where we started, and this question will be addressed in other studies. So, this said, I thank you for your attention and for your time.
Thanks very much, Alessandro. Beautifully clear talk. So, yeah, so we've already had several questions asked during the talk. Of course, if there are any further questions, please feel free to just write them in the YouTube chat window, but I'll just go through the questions that we already have kind of in order. So let's see. So the first question we had was from our own Archak Pukayasta, who said, who asked, can the fluctuation dissipation theorem be proved directly in the microcanonical ensemble without invoking ETH? For example, does it hold in a microcanonical ensemble of an integrable system?
Well, it does, but it's in a different. So there is one paper by Fagotti and Essler that essentially proved the fluctuation, a version of the fluctuation dissipation theorem from for integrable systems. So it does hold, but it's not the same fluctuation dissipation theorem that I wrote down before. Because essentially what is not working for integrable systems is detailed balance, which is the relation between positive frequency and negative frequency values of response functions. Mm-hmm. So that doesn't hold. So you cannot write it in this specific form. But you can write it in some form. So there is some version of fluctuation dissipation theorem for integrable systems. I can tell you later about the reference, but you can check it out. It's a paper, I think, about I would say 2013 by Essler and Fagotti.
Okay, thanks very much. All right, so next question. I think this was a question just about sort of clarification about one of the slides. So when you were introducing the Fisher information and discussing the difference between the shot noise and the Heisenberg limit,
yes.
There was a question in this slide. Yeah, the question was why FQ is missing in the second example. So I think this is why does it not appear in this Heisenberg limit?
Because here essentially FQ is equal to N. So, I mean, I should write it in this way if you want to see FQ appearing. So 4 pi M N FQ, and then FQ for this particular thing would be equal to N. So, I mean, I just calculated directly. While here I just said that for this example, I just said that since you have independent spins, then you do expect your Fisher information to scale like. And in this case, I calculated directly the fluctuations, and they come out to be n squared. So if you want, I know that FQ is equal to n.
Okay.
All right.
Yes, that's clear. Thanks very much. All right. So next question was from Junjae Liu. So the question is, if I understand correctly, so far the discussions are limited to closed systems. Can this framework
Yes.
be generalized to account for open scenarios as the quantum Fisher information is related to non-Markovianity?
Well, that's an interesting question. To be honest, I would have to think about it. I mean, how to generalize it properly. I mean, now I could say some words, but it would not be a satisfactory answer to my taste. So, I mean, the problem is that for open systems, of course, you can generalize the whole concept of quantum Fisher information, but because you have a generic density metrics. But then the question is how to I mean, what would it mean for an open system to discriminate? I mean, all the story that I told you today for an open system would not hold. I mean, the moment you make your system open, it doesn't really matter. You always thermalize to some kind of mixed state. So I'm not sure. I would have to think about it.
Okay, thank you. So let's move on to the next question. We have lots of questions coming in, so I'll try and get through them. So Michael Moskelets asks, how is the shot noise limit modified for a mixed state?
I think it's more or less, it should be more or less the same, right? The shot noise limit for a mixed state. I mean, because the shot noise limit is based on the fact that you have uncorrelated spins. So I think the fact that it should scale, that the Fisher information will scale with n is going to be robust. And what will be modified is f of q.
Yeah, that's correct. I'm sure about that. So okay, thank you.
Thank you, thank you, Professor. I gave the correct answer.
So hold on. Where is the next question? So okay, so I think the next question was from. Oh, by the way, and lots of people clapping and saying thank you for a very nice talk. So have to relay that to
Thanks.
you. So Felix Binder says, great talk. Thanks, Alessandro. Could you comment on the conditions of the local O?
Okay. So the local O. Okay. So so this is something that I completely skipped. So for ETH, it's important that O is what is known as a few-body operator. So what is important in practice, let me mention it, is that this function f of e of omega decays in omega much faster on a scale, let's say omega star, that is much smaller than the average energy, right? And this happens when you have operators that do not have matrix elements between eigenstates that differ by an extensive energy, right? So what are these operators? Well, you can easily figure it out using spins, right? If I take a spin operator like this one in a spin chain, right? Now it's clear that if I pick two states like this one and another one, of course I'm going to have a matrix element only if I flip a single spin. So the energy difference between the states is going to be just a single spin flip. So it's going to be intensive. And also if I pick an operator that is a product of guys like this one, it's going to work in the same way. So it's still going to be intensive. When it's going to be extensive? It's going to be extensive only when I take products of operators that scales extensively. So for example, I take a product for I equal to 1 to, I don't know, L of sigma xi, where L scales like alpha times n, alpha smaller than 1. Well, in this case, then of course you will get matrix elements between states that differ by an extensive energy. But these are quite artificial operators, right? So in practice, all operators that with which experimentalists are dealing with, like densities, magnetization, currents, etc., are few body operators. So I would say ETH and all the story I told you today would hold for those systems.
Great, thanks very much. That's very clear. All right, the next question was from Shane Dooley. Hi, Shane. He says, thanks for the nice talk. Can you say something about how the quantum Fisher information can be measured in experiments?
That's a very interesting question. Well, it's not, so that's a tricky thing, right? So all the story I told you, we tried to think briefly about it. It's not. I mean, of course, I mean you could hope to. I mean, all the bounds, all the Kramer-Rao bounds, are interesting because there exist. So, and this was proven by Braunstein and Caves. In principle, there is a POVM that saturates the bound, right? So since there is a POVM that saturates the bound, in principle, you could do a metrology experiment to measure the quantum Fisher information in the two cases. This might not be very easy, though, right? Because you don't know what is the POVM in principle. So I would say the honest answer is you could try by performing metrology experiments, but yeah, I mean that's where experimentally the quantity is relevant. But how to do it precisely? I mean, if you would ask me, tell an experimentalist now to measure it. I mean, which measurement he should do in order to see it? Well, it's not that straightforward. For me, it would be if someone would be able to see, for example, that the bound that is set by the Gibbs ensemble is violated because you get a better accuracy on your phase estimate. It would be enough of a proof that you have multipartite entanglement or that you have a Fisher information that is relative to a pure state. Yeah. So, I mean, can I just explain one little? I know that there are many questions, but I don't like to leave questions unanswered. So, you see, the problem is the following. You do expect that any physical system, right, that you take, even if it's thermally isolated just for some time, not forever, right? Eventually, it's going to thermalize, to be coupled to something, to see some heating, and it's going to go to a mixed, thermal ensemble. So then the question is, well, suppose that you have a system that stays in a pure state for a while and then eventually becomes mixed. How would you be able to see this? Well, you would be able to see this by the fact that the longer you wait, the more your accuracy in quantum metrology that you can get in a phase estimation experiment degrades. And it degrades because the state becomes more and more mixed. Mm-hmm. So that's essentially what I think. So that's the only experimental thing that can come to my mind at the moment.
Okay, thanks very much. So let me move to the next question, which is from Alvaro Alhambra, who says, does the connection between multipartite entanglement and Fisher information go in both directions? Namely, does a small Fisher info imply low multipartite entanglement?
Does a small Fisher information I don't understand. I'm not sure I fully understand the question.
I guess so. Sorry, go ahead. or would you like me to try and clarify? I mean, I guess the question is whether this kind of connection goes both directions, no? So, I mean, what actually is the statement here? It's that if the Fisher information has a certain value, then there is a certain amount of multipartite entanglement, right?
Yes. So then the question is, if there is a certain amount of multipartite entanglement, does this imply the other way around?
Right, yes.
Well, I don't want to say anything stupid. So again, I would have to think about it, and I'm not 100% sure of the answer.
Okay.
So yeah, I mean, I could say, I could easily say something stupid on this at the moment. So
Okay.
let me skip the answer. I apologize, but you know, sometimes I have to think,
Sure.
and I cannot do it immediately.
Okay, no problem. So I think I got through to the end of the questions. If I may, I'm just curious about one thing actually, which I thought was very interesting. So I'm going to ask the last question, if you don't mind. So
Yeah,
this
sure.
scaling close to a critical point in terms of the critical exponents for a pure state that you showed.
Yeah.
So this is pretty cool. I mean, maybe this is obvious to some people, but it's certainly interesting for me. I was just wondering, like, what does this come about from? I mean, is this scaling related presumably to the
Oh
fact that
no,
the system is gapless, right?
no,
Or
it's very simple, right? It's extremely simple, because you know the thing is, the quantum Fisher information for the pure state, not for the mixed state, is equal to 4 times delta O squared, right? And so if you have, right, if you are in a pure state, what is the operator? So if you think about this maximization process that I'm doing here to connect the Fisher information to multipartite entanglement, what is the operator if I am in a pure state and I go close to the quantum, to a critical point that is going to maximize my Fisher information? The order parameter, right? Because the order parameter has fluctuations that diverge close to the critical point. And this scaling is essentially encoding the way the fluctuations of the order parameter diverge.
I see.
And it's quite interesting that actually, so today, I mean, if you look at the paper, we wrote down this scaling, this expression here. And today, when I was writing down these notes, I noticed that, well, in order to see the connection between this and multipartite entanglement, I should rewrite this exponent here using scaling relations. I mean, the standard scaling relations of phase transitions in some simpler form. And it's quite interesting that what you get using scaling relations is an expression that is always smaller than 1, right? Because if I would get something that is larger than 1, then you would say, okay, but what about the Heisenberg limit?
Right.
Instead, it's always smaller than 1. So it's cute. I mean, I find it interesting.
Okay.
So it's just a very simple story, in a sense.
I mean, I guess what I find interesting about this is that, I mean, typically not all gapless systems would have this kind of scaling of entanglement, right? I mean, there are some systems that are gapless, like integrable models, where you would have short range. You wouldn't expect every particle to be entangled with every other one, right? So, I mean, maybe I'm mixing
Well,
things
but
up here.
you know, but no, but you see a critical. Well, so I think a critical state is a, you know. Well, the point is that a critical state is a very subtle state in which you have. So it's it's a usual story of statistical mechanics. I mean, you have fluctuations on all length scales that are encoded into these divergent fluctuations of the order parameter, and well. So in a sense, what is surprising is that if you try to reproduce this thermal critical state using a pure state, you will necessarily have to use massive multipartite entanglement. This doesn't tell you that these states, I mean, the individual particles are strongly entangled. Typically, when you have a massive multipartite entanglement, bipartite entanglement is actually very weak. So,
Yep.
but it's that's what you need. So I find it interesting. I don't know. I mean, I don't know how to attach better words to it at the moment.
Okay, thanks. No, that's really interesting. All right, so I think it's probably a good time to conclude. So thanks everyone once again for tuning in and for participating. Oh no, sorry, there is a quick question, a final question from
Yeah,
Felix
sure.
Binder. So
Yeah.
Felix says, thanks for the clear answer to my earlier question. A quick follow-up. For few body observables, or maybe almost local observables, is there a modified Heisenberg limit?
No. The Heisenberg limit is, well, so what do you mean? I would need to talk to him. What does he mean by modified?
Right.
So I think the Heisenberg limit is the so I think for local observables, for few body observables of the type I mentioned before, you do have at most the Heisenberg limit. And it's only when you start taking observables that are, but I don't see how you can, because the way I think about it, few body observables are essentially sums of products of operators where the products have a support that is essentially finite. So it does not scale like system size. So at most, the fluctuations that you can get out of this stuff are going like the size of this. So if are going like are going like n squared. I mean, n squared times a factor that is. I mean, there could be something in front because I have a few operators that are multiplied. Yeah, there could be something in front. I don't know, but some constant that does not scale with n. I mean, the n squared is going to stay n squared.
Okay. All right. Thanks very much. Yeah. So let's wrap it up there. So yeah. Thanks everyone for tuning in, of course, and especially thank you so much to Professor Alessandro Silva for a super interesting talk. Thank you.
Thank you. Bye bye.